Are you more or less ready? Okay. Let me just look at this and think about it for a minute. Okay. In his lecture on Monday, Sturl taught us a great deal about the phenomenology of massive black holes in galactic nuclei, about the phenomenology of what happens when galaxies collide and merge. The black holes from the two cores of the two galaxies sink to the center of the merged galaxy, find each other, form a binary, and then we have the possibility of gravitational wave emission by this binary made of supermassive black holes. And so today I want to begin by talking about the gravitational waves from such binaries and their detectability. I'm showing here the Lisa noise curve plotted as a function of frequency going from 10 to the minus 4 hertz up to 1/10 of a hertz. So these are periods of seconds to hours. Plotted vertically is the square root of the spectral density of the gravitational wave noise of the detector, a quantity that we will learn more about in a sophisticated sense from the theory of random processes next term, but a quantity that you have dealt with before. And as you recall, this is something which has dimensions of dimensionless gravity wave strain or gravity wave field per square root of hertz. And you're to multiply this by the square root of the bandwidth over which you collect a signal in frequency in order to get the signal strength, or in order to get the noise that that signal must deal with. I'm plotting in this graph, which graph comes from the paper by Kurt Cutler and myself that's on the course website, a recent review article on gravitational wave sources. I'm plotting the sources in a different way relative to the noise curve than we do for LIGO. The height of the sources above the noise curve in the Lisa case is just equal to the signal and noise ratio that you would get if you integrate up the signal over a frequency band during which the signal sweeps through the frequency band delta f equal to f. So that, for example, sweeping from 10 to the minus 3 hertz to 2 times 10 to the minus 3 hertz, you build up a net signal and noise ratio if you're doing optimal signal processing. And that signal and noise ratio, net signal strength that you build up in that way, divided by the RMS noise in the Lisa band, in that frequency band, is the height above this curve. And so in order to really believe any signal that you see, you need a signal and noise ratio in the case of Lisa of perhaps 5, and so you need to have this signal about a factor of 5 above the noise curve. But in fact, for these massive black hole binaries, the signal strengths are much more than a factor of 5 above the Lisa noise curve. In the case of two 10 to the 4 solar mass black holes spiraling together, you have a signal and noise ratio that may be something like 100. In the case of two 10 to the 5 solar mass black holes, you're getting up close to 1,000. Two 10 to the 6 solar mass black holes, it's getting up toward a number of thousands, maybe 10,000 in signal and noise ratio, and so forth. Let me just remind you about the Lisa noise curve, that at low frequencies we have noise due to stochastic forces acting on the spacecraft. At higher frequencies we have shot noise, and we'll learn all about that next term. Now, and then we also have noise due to white dwarf binaries, which Sturl talked about. Now, returning to the signals from the inspiraling binaries, I'm showing here the signal at a point which is 1 year before the final merger of these two 10 to the 5 solar mass black holes, 1 month before the final merger, and 1 day before the final merger. So you notice that in the period that it takes about of order 1 day to sweep through here, you build up about as much signal as you take in order to go a few months from here to there. So you get roughly equal amounts of signal over the entire frequency band as you sweep from the low frequencies to the high. Now, if you have massive black hole binaries above two black holes that have masses of 10 to the 6 solar masses, you can just extrapolate up here. They will be up there for 10 to the 7, up here for 10 to the 8. But by the time you get down to frequencies below 10 to the minus 4 hertz, we have no confidence at all in this Lisa noise curve. And we probably won't be able to pick up and really believe any signals that we get much below 10 to the minus 4 hertz. So the bottom line is that we should be able to see the in-spiral of massive black hole binaries with very high signal-to-noise ratios up to a few times 10 to the 7 solar masses with Lisa, but it will be problematic to see anything more massive than that because the waves will be pushed down to such low frequencies that the noise will probably rise very sharply down here due to not having a good enough isolation system on the spacecraft, and we just won't be able to see it. Next week, Mark Scheel will give a lecture and talk about the merger waves that come at the end point of the in-spiral down here. Today I want to talk about the waves coming from the in-spiral itself. So let me turn this off and go to the blackboard. Okay. So the issue then is the details of the waves from supermassive black hole binaries. And as we saw, in terms of signal strengths, we should be able to observe the waves when the black holes have masses of 10 to the 4 solar masses, or 10 to the 5, 10 to the 6, 10 to the 7, probably not 10 to the 8. And so let's talk about what we learned from Sterl's lecture last week about these various mass ranges, beginning with masses less than 10 to the 6th solar masses and going on up. And as we learned from Sterl on Monday, for masses less than 10 to the 6 solar masses, we don't know what the event rate is going to be. The reason is because we don't know how many massive black holes there are in galactic nuclei in this mass range. I remind you that the supermassive black hole in our own galaxy has a mass of something like 3 million solar masses, just up above this mass range, and we know about that. We know about a few other massive black holes that are around 10 to the 6 solar masses. But when you go to masses below 10 to the 6 solar masses, you just don't have the observational data. And the reason was, as you may recall, that when you get to these smaller masses, you have smaller cusps in the rise of the stellar dispersion in the spectra from the electromagnetic waves from around from the stars around the black hole. The size physically of the stellar cusp is going to scale as the mass of the black hole. You go to smaller mass black holes and you have a smaller cusp, and you can't see the cusp. You don't have enough angular resolution with the Hubble Space Telescope to see the cusp out to large enough distances to have any more galaxies in your field of view than our own galaxy. And our own galaxy doesn't happen to get down into this mass range. And so it may, however, very well be that there are large numbers of massive black holes in this mass range. Sterl described hierarchical scenarios for supermassive black hole formation based on cold dark matter ideas, in which you would get, if those ideas are right, a large number of black hole binaries in that mass range. But that's speculation. We have no observational data to tell us about it.
In that mass range, does it have to be in galactic cores in these lower supermassive?
It would not have to be. It's a question of astrophysical scenarios. And so you may form things up to maybe 1,000 solar masses, maybe a little larger in globular clusters through hierarchical processes. But I don't know where you're going to get things up above a few thousand solar masses, except in galactic nuclei. But globular clusters you could get up to a few thousand of, perhaps. But if you look at the range of order 10 to the 6 to 10 to the 7 solar masses, that's where we have observational data, and where also the theory suggests that when galaxies such as our galaxy and another galaxy merge, the black holes will sink and find themselves and actually merge in less than the age of the universe. And so we have some confidence about what the numbers are in there, and that's what Stirl talked about. And the bottom line is the various estimates that are made in there range from 0.1 per year to about 100 per year. Is that right? About 100 per year. So there's maybe a factor of 1,000 uncertainty, but that's pretty good in this business. That's an interesting event rate in the sense that even if you don't see the final mergers in the lower end, you might see binary black holes that are headed towards the final merger, but you don't see it this year. You would have to wait 10 years or 5 years to see it. And when you go above 10 to the 7 solar masses, if you look back at that curve, you basically shove the in-spiral waves down to such low frequencies that at least it is unlikely to be able to see them. So this is the really interesting case in the sense that we have some handle on event rate through the processing Stirl talked about. That's very interesting. But involves speculation. The event rate could be quite high, and looking at these could teach us a lot about structure formation and what goes on in the building up of massive black holes. Now, because the signal-to-noise ratios are so strong, and I showed you signal-to-noise ratios in that graph for sources at a distance of cosmological redshift of about 1. Because those signal-to-noise ratios are so high, that means you can see these to redshifts large compared to 1, out to basically the very beginning of structure formation, which was at a redshift of 10 or maybe even as far as 30, that you might have started to form some of these things. And so it's important in thinking about the gravitational waves to pay attention to cosmological effects on the frequencies and the amplitudes of the waves. So I want to briefly discuss that then. I imagine I have some source, 2 black holes orbiting each other, and in the local wave zone, before you're out far enough that cosmological effects become important, we know what the gravitational wave field looks like. H plus, for example, H cross just differs from H plus by a different dependence on the inclination angle of the binary of the line of sight. It looks like 2 times 1 plus cosine squared iota, or maybe we called that theta earlier, where theta is the inclination angle to the line of sight. So if you see it face on, theta is 0. If you see it edge on, the binary edge on, theta is pi over 2. So you get the strongest waves if you see them face on. Times mu over m, where mu is the reduced mass, m was the total mass. I'm sorry, mu over r times pi mf to the 2/3 times cosine of 2 pi ft, where f then is the instantaneous frequency, and f is increasing with time as a result of in-spiral. It's chirping, we say, as the frequency rises as a result of in-spirals. So mu was the reduced mass, and m was the total mass. In the case of equal mass binaries, mu would be 1/4 of the mass of an individual black hole, and m would be twice the mass of an individual black hole. 1/4. No, it would be m1, m2. It would be m1 squared over 2m1. So it would be 1/2 for mu, and the total would be 2m1. So mu would be 1/2 of m1. And m would be 2m1, where m1 is the mass of one of the black holes. So the total mass would differ from the reduced mass by a factor of 1/4, which is the factor that Alessandra Tuanano used in her lecture last time. And I talked always then in terms of reduced mass and total mass. Now, the fact that these waves are propagating from the very early universe, rather early universe to us today, means that they're gravitationally redshifted. And so I'm going to go in here and note that this F that we're talking about is the emission frequency. And this is times the emission time. And up here, this F is the emission frequency as well, because this is what we're talking about in the local wave zone. So thought you were undressing.
Doesn't make a very good pickpocket, does it?
No.
Better don't get the tails out.
Did you turn it on?
Okay, so T
Mihai,
emission
did
is
you
the
turn it
proper
on?
time measured in the local wave zone, and F emission is the frequency of the waves measured in the local wave zone. When the waves reach Earth, so at Earth, where the observer is, the time is measured at Earth. And the time and the emission time differ by, well, let me write it, T emission equal to 1 plus a constant. Okay. And that's the gravitational shifting of T and the observation. So that means that I can go in and up here where I have T emission, and aside from an additive constant that just has to do with basically the time that it takes for the light to travel from the source to the Earth, I can replace T emission by this expression. And so I have that H plus is equal to 2 times 1 plus cosine squared theta mu over r pi m F emission times the cosine of 2 pi. F emission becomes 1 plus z F emission times the time as measured on Earth, the observation time, plus some arbitrary constant, some arbitrary phase shift. No. This is the observed frequency. So the observed frequency is larger by 1 plus z times the emitted frequency. Oh, there's a pi m after the 2/3 there. Yeah, okay. So the observed frequency is 1 plus z times the emitted frequency. Z is the cosmological redshift. And that's just, if you wish, that's the definition of z. It's such that the observed frequencies are 1 plus z times the emitted frequencies. And so we now have the time dependence expressed in terms of time as measured at Earth. That means that we never really directly measure the emission frequency. All we measure is the observed frequency, and we typically will not know what the redshift is, at least not directly from the observations. We may infer it indirectly by means that I'll talk about, but not directly from the observations. And since we don't necessarily know what the redshift is, we don't know the emission frequency, all we know is the observation frequency, I want to re-express the stuff out in front in terms of the observation frequency. And so the observation frequency, just a second, I've got the observed frequency is lower than the emitted frequency, so this 1 plus z should be to the minus 1. Okay, so do I have that wrong up here? This is to the minus 1.
That's fine.
So it's 1 plus z to the minus 1 times. Okay. Damn. Let's go back here and do it right, okay? So we have that F observed is equal to 1 over 1 plus z times F emitted. And we have that T observed is equal to 1 plus z times T emitted, so that the product of F observed times T observed is the same as F emitted times T emitted. That is, they redshift in the opposite direction. Okay. And the observed frequency is lower than the emitted frequency. And so this is cosine 2 pi F observed T observed. And F observed T observed is the same thing as F emitted times T emitted. Okay. Okay, so then up in here, I want to get rid of F emitted, the emitted frequency, because that's not something that I can see. I can only measure the ticking rate of the observed time at Earth, and so I can only infer the observed frequency, and so I want to write the amplitude in terms of the observed frequency. If I do that, then this F emitted becomes 1 plus Z times F observed, and so this expression becomes pi mf, or pi m times 1 plus Z F observed goes in there. Okay. Now the product mu times m to the 2/3, which is the product that I have in here, is just a power of the chirp mass. Recall the chirp mass is mu to the 3/5 m to the 2/5. And so mu m to the 2/3 is just a power of the chirp mass. And so I can also go in here and I can rewrite this whole thing in terms of the chirp mass. This just becomes chirp mass here, and that m becomes chirp mass there. So I claim that chirp mass over r times pi chirp mass f to the 2/3 is the same as mu over r times pi times total mass to the times f to the 2/3. Okay. And so what I then have inside this expression is the observed mass times the chirp mass. I'm sorry, the observed frequency times the chirp mass. So I would also like to write this up here in terms of times 1 plus Z. So what I'm really inferring in here is 1 plus Z times chirp mass from this expression. So I want to express that also in terms of 1 plus Z times chirp mass. And so I can do that by multiplying the top and the bottom by 1 plus Z. Okay. So that has those factors brought into a form that I'm going to want. I'll collect everything together in a moment. But I need to worry about the 1 over r behavior, because this 1 over r was 1 over r in the local wave zone, but cosmological effects are going to change what I mean by 1 over r when I get to large radii. But this waveform has the rapidly oscillating phase part, which is what I have in here that I've dealt with. And the amplitude, we know the amplitude should really die out as 1 over the square root of the cross-sectional area of a bundle of rays. We know in general that the amplitude of the waves dies out as 1 over cross-sectional area of a bundle of rays in the geometric optics approximation. And then it oscillates with the phase oscillation, and the phase oscillation is basically carried along the rays, conserved along the rays, but oscillates very rapidly from one ray to another. We've already dealt with the phase oscillations. We haven't dealt with the fully with how the waves die off with distance. And so this 1 over r factor, in the near zone, this is the square root of the cross-sectional area, in the local wave zone, cross-sectional area of some bundle of rays. What bundle of rays? Well, this is a spherically symmetric situation. And the rays I'm concerned about go out from the source subtending some angle, some solid angle around the source. Now, and so the cross-sectional area then is something that that is a cross-sectional area of a bundle of rays that are spherically symmetric, subtending some solid angle, and they just continue to subtend the same solid angle as they go out through the universe. And so the R that I want to have appear here is the cross-sectional area of that bundle of rays that subtends a unit solid angle. So you can use cosmological theory, cosmological models, to figure out what that R is. That R is what is called by cosmologists proper motion distance. The proper motion distance is, just by definition, it's the square root of the cross-sectional area subtended by a bundle of rays going out in a spherically symmetric situation away from their source. Okay. So I'm going to put a subscript PM on here for proper motion distance. And then I have the final answer that H plus is equal to 2 times 1 plus cosine squared the inclinational angle. I have chirp mass times 1 plus z divided by the proper motion distance times 1 plus z. Then I have pi times chirp mass times 1 plus z. F observed to the 2/3. I have the cosine of 2 pi f observed t observed. So it's evident then from this expression that what we should be able to measure, that what we should be able to learn about from the observations of the gravitational waves, if we have no other information, we can measure F observed. We can measure the chirp mass times 1 plus z. And in fact, if you go through the details, and I'm going to give you an exercise on this, the chirp mass times 1 plus z actually comes out of the in-spiral rate. So if you look at the in-spiral rate, which is not embodied in here, you have to go on and look at the time rate of change of frequency, and then you measure an in-spiral rate, and that gives you chirp mass times 1 plus z. And then knowing chirp mass times 1 plus z, knowing h plus and h cross, which depends in a different way on the inclination angle, their ratio will give you the inclination angle. So you get the inclination angle from the ratio of h plus to h cross. Everything else is the same in the two in terms of amplitude. So that gives you the inclination angle. And knowing inclination angle, chirp mass times 1 plus z, you can get the proper motion distance times 1 plus z. And so these are the things that are observable from this signal. The proper motion distance times 1 plus z, for those who know cosmology terminology, is what's called the luminosity distance. And so we learn the observed frequency from the oscillations, from the in-spiral rate. We learn the chirp mass times 1 plus z. From the ratio of the amplitudes of the two polarizations, we learn the inclination angle, and then from the overall amplitude of the waves, we learn the proper motion distance times 1 plus z, which is the luminosity distance. So those are the things that we get out of the observations. If we look at the post-Newtonian corrections that Alexander talked about last week, then we can get the individual masses as well, but not surprisingly, and this will be an exercise for you, you get m1 times 1 plus z and m2 times 1 plus z. And so you can never directly measure off of these gravitational wave observations alone. You cannot directly measure the masses, but you can get the masses times 1 plus z. You cannot directly measure the proper motion distance, but you get the proper motion distance times 1 plus z, or the luminosity distance. Those are the things then that you infer from the in-spiral waves. Okay. Now it's worth knowing how as a function of redshift, because we're talking about doing observations that might go out as far as a redshift of 30. As a function of z, what does the proper motion distance look like? And what does the luminosity distance look like? Well, of course, both of them start out looking like the same thing, increasing linearly with z. So this would be 0, let's say 1, 2, 3, 4. Proper motion distance goes up and asymptotes to a fixed value. The reason is very simple. If you imagine having a source that's in the early universe, and it's emitting when the universe is, say, 1 billion years old, but we live in the universe when it's 15 billion years old, say. The cross-sectional area of a bundle of rays that have headed out from there over those 14 billion years since then, it'll have some given size. But if you emit the waves from when the universe, instead of being 1 billion years old, was 500 million years old, so the rays travel for a total time of 14.5 billion years instead of 14 billion years, the cross-sectional area of that bundle of rays is not going to be very much bigger than it was in the first case. We traveled for only a tiny fractional increase in distance, but that corresponds to a rather big difference in redshift. And so it's for that reason the proper motion distance flattens out, whereas the luminosity distance rises and keeps going linearly. Since luminosity distance goes as a proper motion distance times 1 plus z, it's got to keep going linearly. It'll have some curvature in here, but then wind up going linearly in the end. Now, the overall strength of the waves in terms of h, it goes as 1 over proper motion distance. Well, I put a 1 plus z in the numerator and a 1 plus z in the denominator, but I only did that because I wanted to talk about what is it that we actually can measure, what can we infer from the observed waves. And it's luminosity distance we infer from the observed waves, but it's really proper motion distance that determines how strong the waves are when they reach the Earth. So the waves, as you go to larger and larger redshifts, the waves get redshifted, the observed frequency gets lower and lower. But the overall amplitude of the waves just doesn't change much for the same source as you go out to larger and larger and larger redshifts. And so that basically means that you can really see these sources that have these very large signal-to-noise ratios at a redshift of unity. You really can see them out to redshifts of 10 or 30 just fine. Okay. Any questions? Okay, then I want to switch over to my second topic, which is the gravitational waves from small bodies spiraling into massive black holes. And so Sturl also discussed to a small degree this issue at the end of his lecture. And he noted that, and I'll probably give you an exercise on this, that if you have black holes in the mass range that we can see the waves for which we can see the waves, and let me say that the wave frequency, which depended on the total mass in the previous diagram, as you make the total mass bigger and bigger and bigger, the wave frequency goes down because it takes a longer characteristic time for the binary to go around and around. And similarly, if you have a small object spiraling into a massive black hole, the bigger the mass of this black hole, the lower the frequency of the waves has to be. If the object orbiting goes down within, let's say, 10 Schwarzschild radii of the black hole, 5 horizon radii. As you make the black hole more and more massive, these distances become larger in proportion to the mass, and so the wave frequencies go down inversely with the mass. And so the bigger black hole, if you inspiral into a more and more massive black hole, you wind up with waves that are at lower and lower frequencies. And so, the numbers are roughly the same as in the case of two inspiraling black holes, since in the two inspiraling black holes I had equal masses, and some of the masses was within a factor of 2, the same as the mass of an individual black hole. Basically, the numbers are roughly the same, And the bottom line is that we can see stuff spiraling into and near the horizon of black holes where the mass of the black hole, which I'm now going to call M, is in the range, say, 10 to the 5 to 10 to the 7 solar masses. But below this, the waves are going to be shoved to a high enough frequency and are going to be weak enough that you can't see it. And above 10 to the solar masses, they're shoved to such a low frequency that you can't see the waves. And so the black hole mass in the range 10 to the 5 to 10 to the 7 solar masses is what we want to think in terms of, and 10 to the 6 solar masses is more or less optimal. And the inspiraling object has got to be a white dwarf, a neutron star, or a small black hole. If it were any other kind of a star, the star would be sufficiently large for this mass of the big black hole that it would be torn apart long before it nears the horizon of the big black hole, be tidally disrupted. And that's what I will give you an exercise on, is for what masses of big black holes would normal-sized stars be torn apart before they get in the vicinity of the horizon. And for what masses do you have, for what masses of big black holes will normal stars get torn apart? And is it true, indeed it is, that throughout this mass range, white dwarfs will get torn apart at the lower end of this mass range, but they get very close to the horizon before they get torn apart. Neutron stars, small black holes will never get torn apart in this mass range. Okay. Now, I want to show you the signal-to-noise ratios for stuff then, white dwarfs, neutron stars, and small mass black holes spiraling into supermassive black holes, with supermassive black hole masses in that range of 10 to the 5 to 10 to the 7 solar masses. And I've just picked one specific set of numbers from which you can scale things. And that's a set of numbers where my big black hole is 10 to the 6 solar masses, and I have a 10 solar mass black hole spiraling in. And I'm showing you two examples. One is where the big black hole is spinning rapidly. So it's described by a Kerr metric, a Kerr's solution to the Einstein equations. The other is where the big black hole is not spinning at all. In the case where the big black hole is spinning rapidly, in the last year, the waves move from a frequency of about 30 hertz on up to about, a frequency of 3 millihertz on up to about 30 millihertz. So it sweeps through a fairly big frequency band, and then as the small black hole plunges in the big black hole, the signal strength falls.
10 minutes to...
Pardon?
Sorry, I just read it. 30 millihertz, about 10 minutes.
So 3 millihertz is a period of about 300 seconds, so it's about 5 minutes. Okay. So a 5-minute period up to a tenth that, so a half a minute period. This is 1 year before the end, and the number of cycles left in the wave train is roughly 180,000. Then 1 month before the end and 1 day before the end. Well, I've forgotten the numbers, but 1 day before the end is a few thousand cycles left in the wave train. The signal-to-noise ratios are pretty big in this case, signal-to-noise ratio of 100. If the big black hole is not spinning at all, then you do not sweep through very much range of frequency at all. 1 year before the end you're here, 1 day before the end you're there, 1 month you're here, and 1 day you're there. So the spin of the black hole has a tremendous influence. That influence arises primarily because the ISCO that Alessandro talked about, the innermost stable circular orbit, for a rapidly spinning black hole, it's at a far smaller circumference by a factor of 6 than for a non-spinning black hole. And so there's a very big difference in the And if the black hole spins very fast, then the in-spiraling object can get very close to the horizon in terms of circumference before it starts to plunge, before it reaches the ISCO and falls in.
Your ability to detect it is really dominated by when it's far away, because that's when you get the most rate.
Well, the signal-to-noise ratio is about the same. This is plotted at a height such that the signal-to-noise ratio is this height, where the signal-to-noise ratio is what you build up as you sweep through delta F equal to F. So and delta F equal to F is about that much. So in sweeping from here to there, you get a signal-to-noise ratio of about 100. From there to there, signal-to-noise ratio of maybe 90 or 80. And so it's really, in fact, turns out that although you have more cycles out, here, you have a weaker signal, and they more or less balance in signal-noise ratio. Pardon?
Get lucky that way.
Yeah. So they more or less balance in signal-noise ratio. Now, what I want you to remember is the number. 10 solar mass into 10 to the 6 solar masses, we have a signal-to-noise ratio that could be roughly 100. So that's very promising at first sight. So that's what I will talk about. Okay. So some numbers. So this is a 10 solar mass for mu. The total the mass of the big black hole is 10 to the 6 solar masses. The signal-to-noise ratio is about 100. If we do optimal signal processing, and we'll talk about precisely what optimal signal processing means next term. But in order to do optimal signal processing, you need to know in advance what the waveform is to within about a radian over the whole sweep of the signal. Now, for reasons that I'll explain in a few minutes, it's unlikely we'll be able to do optimal signal processing for these sources. And as a result, we're going to lose in signal to noise. And we don't know how much we're going to lose. But my personal guess is we may lose as much as a factor of 20. That's a guess. And I could be wrong, and I hope I'm wrong. I hope I'm very wrong. But could lose, Kip speculates, a factor 20 in the signal-to-noise ratio. So that means, if that were the case, that the signal-to-noise ratio we're dealing with is about 5. Now, 5 is good enough that you believe what you see, but only sort of barely. Because these signals last for a whole year instead of only lasting for a few seconds or a few minutes, as in the LIGO case, you don't need nearly as big a signal-to-noise ratio to be confident in the LISA case as you need in the LIGO case. So 5 should be adequate.
That's after you've counted for integration.
That's including the total signal-to-noise ratio that you may build up. Okay. Now let's talk about rates for these sources. And then for that I appeal back to Stirl's talk again last week. So if you follow the population synthesis calculations that Mark Freitag has been doing here at Caltech, those population synthesis calculations are population synthesis basically for the evolution of a cluster of stars around a massive black hole, not for the evolution of a binary black hole systems. But you look at Mark Freitag's calculations, and he computes then for what we think are the kinds of conditions you would have around one of these massive black holes. he computes in the end the rate at which compact objects, primarily black holes that may be 10 solar masses, get swallowed by the big black hole. And then you extrapolate out through the universe, and so the tail end of this analysis is done by Finney, based on Mark's simulations. They will give us then for the case of 10 solar masses going into 10 to the 6 solar masses, they will give us an event rate of 1 to 10 per year, which is very nice. So we feel good. But if we lose this factor 20 in signal-to-noise ratio, and it's at the lower end of that, or even a little below the end of that, I'm sorry, excuse me, that's 1 to 10 per year. At what distance? I didn't write it down, but I think it's out to 1 gigaparsec, out to the 3 gigaparsecs that I had in the diagram. So I was working at a distance of 3 gigaparsecs. That is out to something like a cosmological redshift of order unity. Now, but they may have it at 1 gigaparsec. I've forgotten. But the bottom line is that if these numbers are right, we're probably okay. But this depends on the modeling, on the correctness of Mark Freytag's modeling. And if that is not giving the correct answers, we could be in bad trouble. Bad in the sense that Lisa may not see this source. Now, as I will explain, the glory of this source is this is a source that will enable us to explore the space-time geometry in the immediate vicinity of a massive black hole with very high precision. So we really want this source. So the LISA International Science Team, which basically oversees LISA from a science point of view, of which Tom Prince is a co-chair, the American co-chair, and Sturl and I and Prince are members of it. We met in Italy in December, and we faced up to the issue of this source and the possibility that Finney and Freytag are wrong. And we agreed that they should explore making LISA more sensitive by a factor of 4 than the current design, and see how much it costs, because we're afraid of losing this source otherwise. So this source drives the LISA noise curve, and making it a factor of 4 or more sensitive means scaling up the telescope that collimates the beam, and or increasing the laser light power. There are a number of things you can do that in order to do this, and you would do some combination of these things in order to really achieve this improved sensitivity, but we don't know how much it's going to cost, and that's being costed out. In the meantime, because the LISA specifications need to be frozen by a year from this coming December, in the meantime, there is going to be, I hope, a very strong effort to try to pin down how much loss of signal and noise ratio there is. There will be another problem, and that is the problem of digging the waves from individual ones of these sources out from the background that is caused by all the other sources of this sort and by white dwarf binaries and everything else. That again is a signal processing issue. So both of these signal processing issues are going to have to be worked very hard between now and December 2003 in order for us to firm up the design of LISA. And in parallel, the LISA project is going to be costing the more ambitious design, as well as the old, less ambitious design, to see what the cost is. And it'll all come together December 2003.
This emission on phase the only one?
No, so there are estimations by Sigurdsson and Rees, and I will give you references earlier that do not rely on these simulations, but rely more heavily on observation than on the simulations. And they will give us a rate of a few per year. for neutron stars going into 10 to the 6 solar mass black holes. At roughly this distance, at I think 1 or 3 gigaparsecs distance, I think maybe at 1 gigaparsecs distance. When you look at how the signal strength scales, when you go from 10 solar masses to the neutron star, you basically lose in signal strength by a factor of 3. And this loss of a factor of 3 in signal strength is such that with the more ambitious mission, we should still be all right if these estimates, which are more nearly based on observation than, but not by any means fully based on observation. If these are right, but Finney and Freitag are wrong, we're okay with the more ambitious version of LISA, but we would not be okay with LISA, with the original version of LISA, and the loss of signal and noise that I'm speculating. So there are really 3 issues that need to be understood as best we can by December 2003. One is the event rates. We have these 2 different estimates arrived at in different ways. The event rates, the loss of signal and noise due to not being able to do optimal signal processing, and the loss of signal and noise due to the difficulty of finding the signals in the background of other sources. And all 3 have got